So welcome back for the second talk by Tom in the series. So over to Tom.
Thanks. Thanks everyone for coming again. Let me just try and pull up the chat. So just to quickly recap where we were last time. So we proved a bunch of basic and not so basic things about percolation, which is setting us up for things we're going to do, some more new things that we're going to be doing in the remaining lectures. So one thing we proved is that, first of all, the critical probability PC is always positive on a bounded degree graph. And on a transitive graph, we have at most these three phases, right? So first we have no infinite clusters, then we have infinitely many, then we have one. And again, we don't know that these last two phases are non-degenerate. So maybe there's no phase where there are infinitely many infinite clusters, and we saw this is true on amenable transitive graphs with the Bernoulli proof. And then finally, we potentially have a phase where there's a unique infinite cluster, but this might also fail to happen, for example, on a three-regular tree where we never have a unique infinite cluster except when P is actually equal. Okay. We also saw the sharpness of the phase transition, which remember said that on a transitive graph, if we're below criticality, then not only is the cluster at the origin almost surely finite, which is of course just by definition, but moreover, it has finite expected size as well. Okay. And the last thing we also did was we showed a proof of Benjamini and Schramm showing that on a non-amenable regular graph, we have this upper bound on PC that it's at most 1/1 plus the Cheever constant. Remember, it's this thing measuring the non-amenability. It's the worst ratio of boundary to volume in a finite set times the degree of the graph. So to start today, let's just state one of the big conjectures in the field and then briefly discuss previous work that's been done on it. So the conjecture, which is due to Benjamini and Schramm in 1996, says that the converse of the Burton-Keene theorem that we saw before is also true. So if you have any transitive non-amenable graph, then there should be a non-degenerate phase in which you have infinitely many infinite clusters, i.e. PC should be less than PU. Okay. So the first paper that really studied this problem, and in fact before the general conjecture was formulated, was by Grimmett and Newman in 91 or so. And they looked at an example that they called, well, they looked at the product of a regular tree with a Euclidean lattice. So they were particularly interested in the case that the lattice had dimension 1, and they called this percolation in infinity plus 1 dimensions. Then they proved that in this example, which is just a K large, if you take the tree to have really large degree, then they were able to show that all three phases are non-degenerate. So you really get non-existence, then non-uniqueness, then uniqueness. Once the general conjecture was formulated, most early progress on it was of what I call a perturbative nature. So I'll be showing you some proofs along these lines shortly. So the idea here is that we have this conjecture that says something about all non-amenable graphs. Okay? But what we might try and do instead is, instead of proving it for all non-amenable graphs, let's prove it for graphs that are very non-amenable in some sense. Right? So maybe let's not, instead of assuming that the Cheever constant is positive, maybe let's assume that it's large, something like that. Okay? And there are lots of variations on exactly how you set this up. And often what you can do is prove via some kind of counting arguments some explicit upper bounds on PC. In fact, we already saw a good one, and explicit lower bounds on PU, and then just try to say that if the parameters are favorable enough, we can just explicitly separate PC and PU via these combinatorial upper and lower bounds. Okay, so there are lots of works that approach the problem in this direction. one of the most notable, and we'll actually see a proof of, is by Magnabader and Pack. So they showed that every non-amenable group has at least one Cayley graph where the conjecture is true. Okay, we'll see a proof of this in a minute. Just to briefly overview what else has been done, and we'll come back to some of this stuff later. So the non-perturbative results, the first main thing is a result of Benjamini and Schramm around 2000, following some earlier partial work of Lally, where they solved the conjecture completely in the planar case. Okay, and in the planar case, you have lots of extra tools to play with because you have duality between, well, the planar graph and its dual, and the percolation on the primal and the dual are related, and you have various.
Sorry, Tom, there is a question in the chat box by Mahan saying, what is large Cheeger constant?
Yeah. Of course, the Cheeger constant is at most 1. So I think there are results by, I think there's a result of Schonman which says that if the Cheeger constant is bigger than 1/√2, then the conjecture is true, something like that. We'll see something similar in these lectures, but where we look at the spectral radius instead of the Cheeger constant, which is the Magnabader Pack result. Okay, yeah, good question. Yeah, so of course, these are quantities that can't exceed 1, so they can't really be that large, but we just want to assume they're not too small. So the close to 1 means large. Okay, good. Yeah, so as I was saying, in this planar case, there's lots of extra tools, duality, topological arguments you can play around with. And, if you haven't thought about these things too much before, might be a nice example to get stuck into thinking about yourself, like a tessellation of the hyperbolic. Another case where the conjecture is solved is for Cayley graphs of groups that have cost larger than 1. So this was done by Ross Lyons in 2013. I think with this audience and maybe with some of the other courses that are coming up, this cost thing may be somewhat familiar. So I won't talk about this more now, but this is kind of an ergodic theoretic condition that a group can satisfy, which is enough to guarantee the conjecture, and maybe I'll come back to this later. Okay. So my more recent work, there have been 2 cases where I've solved conjecture. Maybe I'll talk about them in reverse order. So the one which hopefully I'll get to tell you something about the proof of later on in the course is this one of Gromov hyperbolic graphs. So Gromov hyperbolicity is kind of force negative curvature condition. This gives us, again, a lot more geometry we can play around with. So this is going to apply particular to, let's say, tessellations of higher dimensional hyperbolic spaces that aren't covered by these older results. And finally, there's one more setting where we understand things very well, which is actually very surprising, which is the non-unimodular case. So, you know, as when I introduced unimodularity before for transitive graphs, I said, well, you know, this is something that basically holds in all non-pathological examples, and non-unimodularity is a bit of a weird thing that we normally don't think about too much. It turns out actually for percolation and many other things that non-unimodularity is actually an extremely helpful property, and you can really use it to understand a lot about the point. So it's really non-unimodularity is a very special thing. The arguments are different. Certainly many tools that one uses in the unimodular case break down in the non-unimodular case, but actually non-unimodularity is very helpful. And you know, moreover, you have examples like a regular tree, where although the regular tree is unimodular, it has non-unimodular transitive subgroups, like the group fixing an end of the tree. So you can actually treat it as though it's non-unimodular and to use. So I don't think I'll be able to go into that during this course, but I just wanted to mention it's kind of an interesting direction things have been going in, and other people have taken this up as well, showing that actually nonlinear modularity can be. Okay. So before going more into this, I just wanted to mention there's another conjecture which is a bit less well known, which is that which is about. So this is another conjecture of Benjamini and Schramm. I'm not sure whether they formulated it as a conjecture or just as a question, which is that if you have a transitive graph and it's one-ended, so that means that if you delete any finite part of the graph, you're left with a unique infinite connected component. So, for example, ZD with D equals 1 is two-ended because you delete the bit in the middle, you're left with two infinite pieces. ZD with D larger than 1 is one-ended, and say a three-regulatory is infinitely ended. Conjecture says that if you have a transitive graph that's one-ended, it should have PU less than 1. So you should really get this uniqueness phase. This has been proven for Cayley graphs of finitely presented groups by Basu and Benjamini. And of all these conjectures, I don't want to come down too strongly on this, but of all the conjectures that are around for percolation on non-nonlinear groups, I feel like this is the one that's most likely to be false. So if you're someone with a background in group theory, you want to cook up some complicated counterexample that's one-ended, but only in some extremely bare way, maybe still has PU plus 1, this might be a nice problem to construct. Okay. So what I want to do now is tell you about how to get these perturbative proofs of PC less than PU. Basically, it's going to be the Magna Beta pack proof, but I want to formulate it in some more new language and actually get a stronger result using some operator norm language, which is something I've been developing for use in percolation, and it has lots of nice applications and consequences. In particular, it's going to streamline some of the proofs a bit. Okay, so as usual, we have our graph, which is full in particular, and given such a graph, we can always consider the space of matrices with non-negative entries that are indexed by the vertex. Okay, and if I give you such a matrix, you can always define its operator norm on L2 in the usual way, right? So you look at the supremum at the ratio of the norm of M applied to F to the norm of F, where you look at all finitely supported elements of L2. Okay. Now, of course, not every matrix in here defines a bounded operator on L2, and that's fine. It just means that this norm will come out as and similarly, I mean, I'll really only use this in the case Q equals 1 and 2, but we can obviously define a similar operator norm Q to Q as the operator norm, where we consider this matrix as an operator from LQ to LQ. Of course, one could also consider mixed norms where you go from one P space to a different one, but that's not going to come up here somewhere. Okay, and the basic trick that I'm going to use is just to think of this connection probabilities in percolation as a matrix. Okay, so I'm going to define the two-point matrix TP to just be the matrix that's indexed by the vertex set and the entries are given by the connection. Okay, and I'm going to define a new sort of critical threshold P22 to be the supremal value of P, where this matrix defines a bounded operator on L2, i.e. this operator norm is finite. Okay, and the new conjecture, which I've developed and shown some special cases of, is the strengthening of the Benjamini-Schramm PC versus PU conjecture. It says that if G is transitive and non-amenable, then PC should be strictly smaller than PT2. So you should have this phase where you have infinite clusters, but this operator is still bounded. Okay, and just to so some quick remarks here. One is that this is indeed a strengthening of. Let me explain this in the reverse order. Written here. So first of all, this is a strengthening of the Benjamini Schramm conjecture because P22 is, and this should be, is always smaller than PU. Why is that? Well, if you're above PU, so you have a unique infinite cluster, then the probability U and V are connected is just, well, it's at least the probability that U and V both belong to the unique infinite cluster. And by FKG, remember, increasing events are positively correlated, so that's at least the product of the probabilities that U and V both belong to the unique cluster, and this is a constant. So if you're above PU, this matrix has non-decaying entries, and it's an infinite matrix, so it must be unbounded. Okay, so that's just completely triggered. Okay, so if you have PC strictly smaller than P22, then you certainly have PC less than PU, so this conjecture really is a strengthening. Okay. And in fact, in almost all the cases where PC versus PU is proven, the proof actually establishes this stronger claim about PC less than PT2. And there's only one, well, there's two exceptions. So first of all, the Benjamini Schramm analysis of planar percolation doesn't establish this, but those examples are always from hyperbolic, so we do actually know PC less than PT2 for those planar non-linear things because they're hyperbolic and it follows from the other results. The only case where we have a proof of PC less than PU, but not the stronger thing, is for these groups of cost larger than 1. But this is a very soft qualitative proof, and it doesn't tell you anything about calculation. Another remark is that if we were instead to look at the L1 operator norm, then this is actually just the same thing as the susceptibility, i.e. the expected size of the cluster of the origin. And the reason why is that if you have a non-negative matrix, then the L1 norm is just the maximum column sum. And because our matrix is symmetric, the L1 operator norm is the same as the L infinity operator norm, which is the maximum row sum. The row sums of this matrix are just exactly equal to the susceptibility. And we know by sharpness of the phase transition that we discussed before that PC is exactly the point where the susceptibility blows up, right? So if I was instead to look at these L1 or equivalently L infinity operator norms, I would just get that it's the same as PC for any stiff graph. So this conjecture is saying that if we instead look at things from this L2 perspective, we should actually get a different critical answer in the non-amenable case. Okay. So let's start discussing this and see how we can prove this conjecture under some perturbative assumptions, and in particular, let's prove that every non-amenable group has at least one Cayley graph where it's true. So let's suppose we have our graph, and we'll write P for the simple random walk transition matrix. Right? So PUV is the probability that a random walk started at U goes to V in one step. Okay. And of course, we've already been discussing these things a bunch in Miklosh's course. So the spectral radius of the graph, rho of G, is defined to be this L2 operator norm of this transition matrix P. Okay. And it's a famous theorem of Keston that non-amenability of a graph is equivalent to it having spectral radius strictly smaller than 1. Okay. And maybe just to mention that this is equivalent to return probabilities decay exponentially. Okay, so in amenable graphs, you have sub-exponential decay of return probabilities, and you have spectral radius 1. Non-amenable, you have exponential decay, spectral radius more than 1. Okay, and just a totally trivial observation that when G is regular, and of course, again, mostly interested in the transitive case where we obviously have regularity, then P, the transition matrix of simple random walk, is related to the adjacency matrix of the graph. A is just equal to K times P. Okay. Now, the extremely basic observation is that for any P, the two-point matrix, the matrix of connection probabilities, is bounded entry-wise by the geometric sum of P times the adjacency matrix. Okay. Where generally I'll use this kind of squiggly inequality between matrices to mean an entry-wise inequality. Okay, now why is this true? Well, we know that if we take the adjacent tree matrix to the power I and look at it at UV, that is just the number of paths that go from U to V that have length I. Right, so in particular, it's an upper bound on the number of length I simple paths, right? Paths that don't visit the same vertex more than once that go from U to V. Okay, now each such simple path, again, is open for percolation with probability P to the I, right? So what we get is that the expected number of open simple paths from U to V is exactly equal to this geometric sum of matrices evaluated at UV, right? And then we just use Markov's inequality because, of course, the probability that U is connected to V is at most the expected number of. But this is just a trivial thing. Now, let's notice that if M and N are non-negative matrices that are, so they have, in that they have non-negative entries, and they're related via this entry-wise inequality, then in fact their operator norms must be related as well. Okay, this is just easy to see from the definitions because if you have a non-negative matrix, then the best F to choose when you're computing the norm is always an F with positive or non-negative entries. And then you just observe that you get a larger quantity. You do it with N. Okay. So what that means is that here all our matrices are non-negative, so we can take this entry-wise inequality and deduce the same thing as an inequality of norms. And so what you get is that the operator norm of TP is always bounded by this geometric sum, right? Because you can use the triangle inequality for norms. So you get that this is bounded by 1 over 1 minus P times the adjacency matrix. Okay. So in particular, so this is finite when P is strictly smaller than 1 over this operator norm. Okay. So we get that P22 is at least this, which is equal to 1 over K times the spectral radius theta. Okay, because A is just K times the transition. Okay. So now we can very easily use this together with the upper bound on PC that we saw last time to prove essentially the theorem of Nagnabeder and Pack, but stated in this strong form in terms of P22 instead of PU. Okay, which is that if we have any regular graph and it has spectral radius at most a half, then PC is strictly less than P22. Okay, so this is an example of one of these perturbative results where, you know, we'd like something like this to hold just under the assumption of non-amenability, although with transitivity as well. And here we're getting that the result is true under the stronger assumption that spectral radius is almost a half. Okay, so how does this go? Well, first of all, let's just write down these two inequalities that we have. So we just proved that P22 is at least 1 over the degree times the spectral radius. And we saw last time that PC is at most 1 over 1 plus the degree times the Cheeky constant. Okay, So now what we'll do is we'll note a standard inequality that the Cheeger constant is at least 1 minus the spectral radius. Okay, and this is the easy part of something called Cheeger's inequality, which also has another bound on the other side that is how you prove that non-amenability is equivalent to having radius less than 1. Okay, so how does this work? Well, if we look at, let's say, take K to be any finite set, right? And we look at this ratio of the size of the boundary to the volume. And remember, the volume in the Cheeger constant we defined in terms of the sum of the degrees, but here we have a regular graph, so it's just K times the number of vertices. Okay. And what you can do is you do a little bit of algebra and you see that this ratio is just the same thing as 1 minus this thing, where I take the sum over all pairs of vertices u and v in the set of p u v. Basically, I'm saying that this boundary edges is just the total number of edges minus the ones that are internal. Okay, and then you're dividing by this 1 over k. Okay, and then you express this in L2 notation as this inner product, right? And then you just use the fact that, you know, use the definition of the operator norm, you can pull out a factor of rho here, and then you get the inner product of the indicator of k with itself, which of course is just the number of vertices it cancels to this. So you get that this ratio is at least 1 minus rho. Okay. You know, this holds for every k, so therefore the Cheeger constant is at least 1 minus rho. Okay. So if you take this inequality and you plug it into this bound on PC, what you get is that PC is at most 1 over 1 plus 1 minus the spectral radius times k, which is strictly less than if I ignore the 1. Okay, whereas P22 is at least 1 over the spectral radius times k. So of course, if rho is less than a half, then you get the inequality that you want, and we're done. Okay. Good. So as a corollary, we get easily, well, depending on how you interpret the statement, we either get easily or we have to do a bit more work to prove that every non-amenable group has a Cayley graph where PC is strictly less than P22. Okay, and this is easy if we allow ourselves to look at Cayley graphs with generating multi-sets instead of generating sets. It's also true if you have to have sets rather than multi-sets, but it's harder and we can do it. Okay, so what do I mean by that? So I think we hopefully saw a definition of Cayley graphs at some point in one of the other courses, but you know, or in Mitlosh's course rather. So a Cayley graph is just a graph that has a vertex set given by the group, and the edges are given by, well, you're allowed to multiply on the right by elements of the generating set. Okay. And of course, you can also consider Cayley graphs with multi-sets of generators. So you're allowed to have the same generator multiple times in the set. And of course, that just means that you have two edges in parallel. And the nice thing about doing it that way is that if you take your generating set and you take a power of it, but consider it as a multi-set. So if you can write the same thing, same elements as a product of k elements of S in multiple different ways, you get multiple elements in your multi-set. Then this has the property that if you take the Cayley graph associated to the power of S, so S to the k as a multi-set, right? Then the random walk on that Cayley graph is doing exactly the same thing as if you take the random walk on the Cayley graph you started with and just run it k steps, right? Because that's just exactly how it's working. Okay? And the nice thing there is, of course, that if you take this the random walk transition operator for the random walk on this S to the k Cayley graph, right? Then it's just the original random walk transition operator to the power k. Okay? So in particular, the original random walk transition operator had spectral radius strictly less than 1 by Custom's theorem. So this new Cayley graph with the power of the generating set is going to have whatever the original spectral radius was to the power k. Okay, and the only important thing about this for us is that this just goes to 0 as k gets larger. So we can take k big enough and find that the spectral radius is less than a half. Okay, so this is just saying that every non-amenable group has a generating multiset where the spectral radius is arbitrarily small. Okay? And therefore, by what we've just seen, you have a generating multiset where DC less than BT2. Okay? Now, it turns out that it is also true that every non-amenable group has a generating set, like not a multiset, but really a set where the spectral radius can be made arbitrarily small. But this is a harder thing. This was proved by Andreas Thom in 2013. It's not extremely hard, but it's not really either. Okay, good. So that's one nice thing you can do with this operator theoretic approach is it just gives you a good language of notation for discussing even some more classical things like this. Later on, we'll see that we can get a lot more out of this approach as well. One thing I just want to mention before we move on that's very useful. So we saw just now this inequality that says we can bound the percolation two-point matrix by this geometric sum of adjacency matrices. And one way of thinking about this is it says that percolation is always kind of bounded by so there's another version of this, which is also very useful, which says that if I want to see what the effect of increasing p by a bit is, I can bound that in terms of a similar geometric sum. Okay, so Tp plus epsilon is bounded by this geometric sum of epsilon times Tp times the adjacency matrix to the I times Tp. Okay, so this is going to be useful in particular when we're below P22 and everything's kind of bounded, and for small enough epsilon, these geometric sums are going to converge. The proof of this is very simple. Basically, the idea is, right, we have this coupling of percolation of P and of P plus epsilon, right, where roughly some epsilon additional edges open up when we go from P to P plus epsilon. Okay. And so you can imagine exploring the cluster of the origin in P plus epsilon percolation the following way, where you first compute what the cluster of the origin is at level P, and then you'll see, oh, there'll be some edges which were closed at level P, but open up at level P plus epsilon. So I'll draw these in blue. Okay. And then, so you see what those edges are. And then you do the same thing again. So the other endpoints of these new edges are going to have their own cluster level P, and you explore those clusters, and then you keep repeating this. So those new clusters that you explore are going to have themselves some edges in their boundary that are closed at level P but open up at level P plus epsilon, and so on. Right? And basically, the I here in this sum is going to correspond to the number of these blue edges that you take that were closed at level P but open up when you go to level P plus epsilon. Okay. So if you want to make this precise, one way to do it is to say, well, the event that X is connected to Y in P plus epsilon percolation, I can write as being included in this big union of disjoint occurrences where, again, I is going to be the number of these blue edges that flip I'm going to use. And I have some collection of I edges, and the first one X to be connected to the first endpoint P1. And then I want P1 to be open at P plus 1 but closed at P. And then I want its other endpoint to be open to the next one, and etc. Okay. And then if you want to deduce this inequality, you just take a big union bound, and then you apply the BK inequality to bound each thing. Well, that's not quite right, because what's the BK inequality? So remember this notation here, this little circle. This means the disjoint occurrence of events, right? So it means that the events hold, and you can find a witness for each of the events, witnesses for each of the events, i.e. sets of edges where if I see what the percolation configuration has done there, I know that the events hold. So for example, these witnesses would be like this path here, and then some path here, etc. Right. The BK inequality says that if you have increasing events, then their disjoint occurrence is bounded by their product. Now, in fact, this is actually true not just for increasing events, but for arbitrary events. This is called Rightness Inequality, but it's much harder to prove in the BK. And here, this inequality, that this event here is not increasing, so we have to use Riemann. Okay. You don't really need to use Riemann. I mean, this is a very high-powered way of proving something very simple, but this is one way of doing it that avoids us going into more details. Okay. So again, once we have an inequality like this, we're free to take norms on both sides and compare norms. And what you get is that at any q, so again, we'll consider this in the case 1 and 2. The operator norm of p plus epsilon is bounded by the operator norm p over 1 minus epsilon times the operator norm of the adjacency matrix times the operator norm of pp. Okay, and this is true for epsilon that's smaller than the rest of the. Okay. So there's a bunch of nice things you can get out of this right away. So one thing is something you may have been wondering about. So we proved before that the susceptibility is finite below PC, right? That was the sharpness of the phase transition. It's trivially infinite above PC because you have an infinite cluster with positive probability. But in fact, this also shows that it's infinite at PC, right? Because essentially what this tells you is that the finiteness of the susceptibility is an open condition. So if you're finite at P, then it will still be finite when you increase P. Okay. And moreover, you even get that as you approach PC from below, if you're at PC minus epsilon, this operator norm, sorry, the susceptibility must be at least 1 over epsilon times the maximum degree. Why is that? Well, if it wasn't, then you could use this inequality and you'd find that this quantity was still finite. So this is saying the susceptibility always goes up at least like 1 over epsilon. And as you approach PC from below, this is what's called a mean field lower bound, in that this inequality is actually sharp in sort of high dimensional settings. This is really the right order that things blow up. In low dimensions, it won't be sharp, but it's still true. Okay. And of course, you can do exactly the same thing with these other operator norms. So you find that at P22, you must have infinite L2 operator norm. And similarly, that as you approach P22 from below, this operator norm has to blow up at least like 1 over epsilon. Okay. And we'll see later on that this is actually a really useful thing. It plays an important role in the group of PC less than P22 for hyperbolic. Okay. Well, so we'll return to some of this operator theoretic stuff later. But what I want to do now is start talking about critical behavior of percolation. So, of course, we know by the definitions that PC was defined so that below PC there are no infinite clusters, and above PC there's at least one infinite cluster. So one of the most natural and important questions is just, well, what happens in PC? Do we have infinite clusters or not? And it's conjectured very, very broadly that you should not have any infinite clusters at PC, provided that it's really less than one. But this is a big open problem, particularly, for example, on Euclidean lattices. So, for example, for the three-dimensional Euclidean lattice, this is a really famous open problem. But ideally, we'd like to show that there do not exist any infinite clusters at PC. And then we'd like to go further and start to understand what these large finite clusters look like. Like, what's the distribution look like? And it's expected that they have all kinds of interesting fractal-like properties. Okay, and many aspects of this fractal geometry that the large finite clusters are expected to have is captured, or is expected to be captured, by what we call critical exponents. So the idea here is that if you look either at criticality and you look at the tails of some interesting random variables, they should have power law tails, or similarly you look near criticality at the rate something's blowing up or going to zero, and these again should be described by some kind of power laws. Okay. So for example, if you look at the probability that the cluster at the origin at criticality is bigger than n, this should decay like some power of n, which is traditionally denoted n to the minus 1 over delta, or the delta is not small. And similarly, like if you start at PC, you expect there to be no infinite clusters, so the probability the origin is infinite cluster should be 0, and then you want to say that it's increasing as you go away from PC, like some power of epsilon. Okay. And another important one is gamma, which is supposed to describe how this susceptibility blows up as you approach PC from below. As we saw just now, this always blows up at least like 1 over epsilon, and in general we expect it to be described by some power of epsilon. Okay. But proving these critical exponents exist is a really hard problem in general, and you know, there's no reason a priori that they should exist, and computing them is potentially even harder. One situation where we can do everything easily, though, is on a tree. So if you take a k-regular tree with k at least 3, then critical percolation on a regular tree is just the same thing as a branching process, right? It's just like a binomial branching process. And you can compute what everything is completely explicitly, and you find, for example, that the probability that the critical cluster at the origin has size at least n decays like 1 over root n, right? This is just the probability of a critical branching process having large progeny. And if you can compute all the other things as well. So in particular, as you approach PC from below, the expected size of the cluster at the origin is really blowing up exactly like 1 over epsilon. We saw the lower band always holds, but here we have a matching problem as well. What about ZD? So here things get more complicated, and the idea is that once you get in high enough dimensions, the lattice should be somehow so spacious that critical percolation kind of doesn't realize that it's not on a tree in some sense. And all the exponents should be the same as they are on the tree. And this is, I'll say more about this in a bit. This is a very kind of subtle thing. This is expected to kick in when you're above 6 dimensions. So above 6 dimensions, there's so much space, you just get the same behavior on the tree, and all these exponents should be the same as they are on the tree. And this is what's called mean field critical behavior. And this was actually proven, at least for D very large. One often hears that they proved it for D larger than or equal to 19, but I think this was never actually written. So it was proven for D very large by Hauer and Slade in the 90s. And then the same method has been pushed down by Fitzgerald and Hofstad, who did lots of computations and computer assisted proofs and so on, and they push this down to D at least 11. This is expected to hold 7 dimensions. However, once you get below 6 dimensions, the model should really feel that it's in this finite dimensional lattice and it's constrained enough that it really starts behaving in a different way. Okay. In 6 dimensions itself, which is like what's called the upper critical dimension, so it's where you switch from having the mean field behavior to not having the mean field behavior anymore. It's supposed to be almost mean field behavior in that you get the same exponents as on a tree, but you get various polylog factors in there as well. But once you're really below 6 dimensions, we expect the exponents to be different. And understanding this seems to be an extremely hard problem. The only situation where we do understand it is for in 2 dimensions, and specifically site percolation on the triangular lattice, where there have been many important works by lots of people that have established what these exponents are. Here you get all these kind of weird rational numbers. So in particular, they're not the same as the high dimensional ones. And these exponents are expected to hold for general 2-dimensional lattices, but the proofs so far may work this specific one. This is all a bit tangential to what I'll be talking about because I want to tell you about non-amenable stuff, which is really this high-dimensional picture. But these exponents, they were predicted to hold a long time ago in the physics literature. They're related to lots of other things physicists care about, like Coulomb gases and conformal field theory, etc. And the proofs of that exponents hold are related to theory of conformally invariant scaling limits, SLA, and so on. This is all very special stuff that's going on in 2 dimensions. On the other hand, if you're really in intermediate dimensions, like especially 3, 4, 5, we really have no idea how to prove anything. It's open even just to prove that there isn't an infinite cluster PC. And there are no conjectures about what the values of the exponents should be or anything like that. Even in the physics literature, the best they can do is give some heuristic arguments of what the exponent should be up to 1 or 2 decimal places, something like that. And there's no reason to believe that they should be nice numbers. But in particular, there's no reason to believe they should be rational if they are in 2 dimensions, or even that they should be algebraic. They just some horrendous numbers that it's hard to sketch about. Okay. So, as I said, this phenomena that the exponents stabilize to the mean field values in high dimensions is quite a subtle one. And maybe you might think that it would be more plausible that they would kind of converge to the tree ones or something like that. But they really stabilize exactly these mean field values after 7 dimensions. And intuitively, what's going on? Well, let me try and give a few explanations. So one thing is that...
sorry, Tom.
Yeah.
There's a question in the chat box. I think 2 questions, probably.
Yeah, that's a good question. So the one from Nishant about why 6 is expected to be the critical dimension. There are heuristics, but not one that I can rapidly explain to you now. I might be able to say something more about the specific value 6 coming up later, maybe. And Mahan, so it should be that it does only depend on the dimension. Certainly in this high dimensional thing, it should be that once you have a transitive graph of 7-dimensional volume growth, that's sufficient for mean field behavior. But that's certainly not known. This is something people have been interested in trying to get to work for a while, and get these high-dimensional ZD proofs to work for other geometric settings, and this hasn't been done. But it should be true. So one thing that's going on is that in high dimensions, somehow percolation behaves similarly to branching random walk. So that's a good way of thinking about what these mean field results mean. You can imagine percolation and branching random walk are quite similar things, right? So you have some cluster. So branching random walk is just where you have particles that are branching and also, so they're splitting and walking at the same time. And percolation almost does the same thing, except when this branching random walk comes back on itself, it's not allowed to branch anymore. Yeah, that's sort of what percolation is. That's one way of thinking about it. Basically, what this mean field stuff is saying is that in high enough dimensions, this sort of self-interaction that the percolation has that forbids it coming back on itself is no longer significant to what it does. Okay, and this is related to it just being harder in higher dimensions for random walks to come out. Another way you can think about what's going on intuitively is that in low dimensions, macroscopic cycles should play a significant role in the large-scale geometry of critical clusters, but they should not in high dimensions. So in particular, I think this is actually an open problem, but if you take, if you look at ZD with D large, and you look at the cluster at the origin, you condition it to be really large, right? So it's finite almost surely, but condition it to be really large, then what you see should look like this picture on the right, which is Albus's continuum random tree. Okay, so if you just look at this graph as a metric space. Okay, so of course the graph is not literally a tree, because it does contain cycles, but these cycles should be essentially irrelevant to the large-scale geometry. On the other hand, in lower dimensions, if you do the same thing, you take a critical cluster and you condition it to be really large, it'll have lots of big cycles that really play a non-negligible role in the macroscopic. And this is ultimately what's underlying the difference between these low-dimensional things and high-dimensional things. And of course, again, this is just ultimately it's all related to the fact that it's harder to form large cycles in high dimensions. Okay, but we'll see some slightly more concrete explanations in this direction. So of course, non-amenable things are as high-dimensional as possible in some sense. We very strongly believe that every transitive non-amenable graph should be mean field. In fact, it should be enough for the graph just to have at least 7-dimensional volume growth.
So Tom, there is another question in the chat box.
Yeah. I'm not sure. So you mean the number of spanning trees on a ball? I don't think so. I mean, I think that will, roughly that will come down to the same thing as the growth of the ball. So I don't think spanning trees are directly relevant though. I mean, I guess that's just, if you take the log of that quantity, it's going to be roughly the volume of the ball. So in that sense, it should depend on it, but I don't think trees are very relevant. Okay, yeah, so it should just be enough to have this 7-dimensional volume growth. So non-amenability should be way more than you need to prove this, but still we don't know how to do it. Okay. So what I want to do next is start telling you how you might prove some things about mean field critical behavior, and also how we can do it under this assumption of PC less than PT2. So remember, we called the expected volume of the cluster at the origin the susceptibility, and this is normally denoted by chi of P. Okay. Now, by Riddhipratim's formula, we get an expression for the derivative of chi of P, which, well, because we can expand this out as the sum of connection probabilities to individual vertices and then differentiate each one, we get that this is 1 over 1 minus P, times this thing in terms of closed pivotal. So it's a sum over x, the sum over edges E, of the probability that E is a closed pivotal for the event that the origin is connected to x. So in other words, the origin is connected to one endpoint of E, and x is connected to the other endpoint of E, but they're not, but the origin and x are not connected to each other. Now, of course, if you really want to prove this properly, you have to do a little bit of analysis to justify it, because Rousseau's formula, as we stated it, is only true for events depending on finitely many edges. Right? So in general, this quantity might not even be differentiable. But you can justify this, and it's not very interesting, so I don't want to go into it. So if G is unimodular, then we can transform the sum using we can get an equivalent expression for the same sum using the mass transport principle, where we're going to swap the roles of the origin and this vertex here. Okay? So if we do that, we get that the derivative is equal to the sum over edges adjacent to the origin, pointing out with the origin, with this quantity, where we take the product of the volume of the cluster at the origin and the cluster on the other end of the edge, given that these two clusters are distinct, so given that this endpoint of the edge is not connected to this endpoint of the edge. Okay. So this gives some nice things right away. So one thing you can get is that the derivative of the susceptibility is always bounded by a constant as the square of the susceptibility. Why that? Well, basically, this conditioning that, well, it's not a conditioning, it's just multiplying by the integrated function, but you know what I mean. If you do condition the two clusters to be distinct, this is like negative information, and it tends to make these clusters smaller than if they were just independent. And of course, if they were independent, then you would get exactly the susceptibility squared here. Okay? And this is not hard to justify. For example, you can do it using the BK. Okay. Now, once you have this differential inequality, you can integrate it. So you can do a bit of calculus, and I'll actually do this for the reverse one in a minute. You find that the susceptibility has to blow up at least like one pixel. In fact, we already saw this, right, by a very different proof just a minute ago, but here we're seeing it through these as well. So usually, if you want to prove that some graph you're interested in has mean field critical behavior, the key step typically is to prove that the complementary differential inequality also holds, i.e. that the derivative of the susceptibility is at least some constant times the square. This should give you more intuition about why things are going to become mean field in high dimensions. The point here is that we'd like to say that these two clusters are roughly independent, even though they're conditioned not to intersect each other. And the point is that in high dimensions, this conditioning not to intersect is a pretty mild condition, because these clusters don't really like to intersect each other that much anyway. So it's plausible that in high dimensions, this expectation is going to be of the same order as if these two clusters were just independent, which is what we want to get this reverse differential inequality. On the other hand, in low dimensions, this condition, this indicator saying that these two clusters don't intersect is a serious thing. It's going to really affect the distribution in a serious way. Right? So we would expect the derivative to be smaller as a result in low dimensions than in high dimensions. So just to keep ourselves honest, let's just do the calculus and see how I can prove if I have a differential inequality like this, a lower bound on the derivative, how do I get this upper bound, right? I want to 1 over x on upper bound for the set of susceptibility below PC. Okay, so here's how you do it. It's very simple, but just so you know that it is simple, let's do it. So first of all, you can write the derivative of 1 over the susceptibility, right, is minus the derivative of the susceptibility over the square root of the susceptibility, right? And that's almost minus c. C is this constant here. Okay. So that means we can, if we integrate this differential, this very simple now differential inequality between PC and PC minus epsilon, right? We get that this function evaluated at PC minus the same function evaluated at PC minus epsilon is bounded by the integral of this, which is minus c epsilon. Okay, but we know that at PC the susceptibility is infinite, so this is just 0, and then you rearrange and you get this unbound on susceptibility that we wanted. Okay, this is actually pretty easy, but now you know that it's easy. Good. Okay. So there's a standard way of proving this mean field differential inequality. It's a sufficient condition for mean field behavior that was introduced by Eisenman and Newman and is known as the triangle condition. Okay, so what they did is they defined the triangle sum P to be, so you fix the origin. So I probably said this before, but I'm always just going to take like O to be an arbitrary fixed vertex of my graph, which I call the origin. Okay, and the triangle sum, you just fix the origin, you sum over all y and z with the probability the origin is connected to y is connected to z is connected to the origin. And just to stress, this is really a product of probabilities of non-independent events. It's not a probability of an intersection. And one nice thing about our new matrix notation is we can express what this is very easily. All we're doing is cubing our two-point matrix and then evaluating it on the diagonal. Okay, and what Eisenman and Newman proved is that if this triangle sum is finite, then well, I could have said then you get this complementary differential inequality. So in particular, this the susceptibility blows up at most like 1 over epsilon, and in fact, it's now known that the triangle, this is known as the triangle condition, the triangle sum being finite at criticality. This is now known to imply lots of things about mean field critical behavior, so many of the other exponents as well. I'll focus on this susceptibility one. It's sort of the one you get most direct control of, and it's one, turns out to be one of the most interesting ones. So one nice thing for us, of course, is that this works very well with our operator theoretic stuff because, well, again, we're just cubing the matrix and evaluating on the diagonal. So if this matrix has finite norm, then its cube has finite norm and therefore has finite entries, right? So certainly this, if PC is less than PT2, then this triangle condition is going to hold. So that means that PC less than PT2 is a sufficient condition both for non-uniqueness and for mean field critical exponents. What I want to show you now is actually a new proof of a new derivation of mean field critical behavior. So I actually have a new proof that the triangle condition implies mean field critical behavior. I'm not going to show you that though. I'm going to show one nice thing of this new proof is that it gives actually a very simple proof that PC less than PT2 implies this mean field critical behavior. So I'm going to show you that instead. But with a bit more work, you can turn this into a general proof that the condition implies this reverse differential inequality. So how's it going to work? Well, we're going to look at this quantity psi p of s, which I'm going to define. So it's picture. So s is some set. I'm summing over edges in the boundary of s of this probability that, so summing over vertices that don't belong to S, of the probability that the other endpoint of this edge E is connected to Y by an open path that doesn't go through any of the vertices of S. Okay? So this sum we're defining to be psi p of S. And by Ritter's formula, again, we had this expression for the derivative in terms of this sum over pivotal or pairs of pivotal edges and vertices that they're pivotal for the connection to, this kind of picture. And of course, you know, with this quantity psi p of S, this is just the same as saying that we're taking the expectation of what we get when we plug the cluster of the origin into this function psi p of S, right? Because once I've explored the cluster of the origin, all the edges which are not incident to it are still just ID standard percolation, right? Their distribution hasn't been affected by us revealing the cluster of the origin. Okay, so because of this equality, it's going to suffice for us to prove under this PC less than PT2 condition that psi p of S is always lower bounded by a constant times the susceptibility times the volume of S, right? Because then I can just, in this expectation, I can pull this out. I just get the expectation to cluster at the origin, and then I end up with the square of the susceptibility like I wanted. Okay. Now this inequality, this pointwise inequality, the proof of this is really going to use this stronger assumption that PC is less than PT2. Okay, so if you only have the triangle condition, then you don't expect to have like a pointwise inequality for every set like this, but you can still get this proof to work. The idea is going to be that this inequality kind of typically holds for that you actually get as the cluster of the origin. So, okay, so now we want to prove this, and we'll see that actually it comes down to making the right observation and then just messing around with some Cauchy-Schwarz model. Okay, so let's fix some set S. And now let's notice the following. Suppose I take some vertex x belonging to S and some vertex y that does not belong to S. Okay. Now, suppose that x is connected to y. Right, then if we look at the path from x to y, or look at a path from x to y rather, an open path, there must be some last time that it visits S, right? So maybe it looks something like this. Okay, and if you look at that edge E that it crosses as it exits S for the last time, then what you get is that the portion of the path up until you visit the other endpoint of E, and the portion of the path after E plus, well, they're obviously disjoint. Right? So what you get is that these things are disjoint witnesses for the event that X is connected to E minus and that E plus is connected to Y off of S. Okay, so no matter where this path is, there must exist such an E so that we get these disjoint witnesses. And that means that the event that X is connected to Y is contained in the union of edges in this pointed edge boundary of S at this disjoint occurrence of the three events, that X is connected to E minus, E is open, and E plus is connected to Y off of S. Okay, so if you do a union bound and apply the BK inequality to bound this probability of the disjoint by the product, then what you get is, so also we're going to sum over all pairs X and Y. So on the left-hand side, we get the sum over all these probabilities, X in S, Y not in S. Then on the right-hand side, we're going to get this sum where we're also summing over this edge E in the number, right? And we get this factor P, which is actually not really important at all. And we get the probability X is connected to E minus, and the probability E plus is connected to Y off of S. Okay? So again, this is just union bound and BK inequality from this inclusion of that. Okay. So now what we'll do, in order to clean up our notation a bit, we'll define f of a vertex v to be, well, 0 if v is not in it, and otherwise we'll define it to be this sum that we're getting over edges that are in the boundary of S and start at V, and then the sum of y not in S of the probability E plus is connected to y off S. Okay. So if we use this notation, we're going to simplify this inequality just by using the notation, so we get that this sum connection probabilities with X in S, Y not in S, is upbounded by P times the sum over V in S of and the sum of f of v times the sum of x in this connection. Okay, which we can write in L2 notation as p times the inner product of Tp applied to the indicator function of S and producted with f. So now what we do is we found this inner product by pushing products, right? And then furthermore, this L2 norm of f, well, it's just the square root of the sum of squares. So I can always bound that by the square root of the sum times the square root of the maximum value, right? i.e. the square root of the one norm times the infinity norm. Okay, so I mean, this is the case of Holder, I guess, but it's also just a trivial thing. Okay. So that gives us an upper bound on the right-hand side that's going to be useful. On the other hand, for the left-hand side, well, the sum of x in S and y not in S, well, if we were instead to sum over all y, right, then for each x, we would just get a copy of the susceptibility, right, because we'd be fixing x and summing over the connection probabilities for all other vertices. And so if we summed over all y, we would just get the number of vertices in S times the susceptibility, right, but we have to subtract the vertices that we're not summing over, so the y that are in S, but this in our L2 notation is just this inner product. Okay, so now on the other hand, if you look at this function f of v, if you take this L1 norm, i.e. if you just sum this over S, this is exactly this quantity psi p of S that we're interested in. So what you get is that psi p of S is the same thing as the L1 norm of F. And if you rearrange these inequalities, what you get is that it's lower bounded by the ability times the volume of S minus the product, all squared, divided by p squared times this norm times the infinity norm of F. Okay, now let's look at F again. So we had this indicator function, and then we had the sum of things, and then summing over y not in S. Anyway, the point is that we can certainly bound this by the degree of v times the susceptibility, right? Because we get at most degree v of these edges that we might consider, and then this sum we can bound. First of all, we can just forget this condition that we're doing things off of S, and just sum over all y instead of only the y that norm S, and we get this. Okay. So for the infinity norm of F, is certainly bounded by the maximum degree times susceptibility. Okay. Now, what you can now do is, bound this norm and this inner product just using the operator norm, right? So, of course, I can just pull out the operator norm and then have this obvious equality that the square of the norm of the indicator function is just the size of the set. And what you get is this lower bound, right? That psi of p is at least susceptibility minus the operator norm squared times the size of this squared, and then the denominator, I guess I'm supposed to p squared here as well. Yeah, this doesn't really matter. The point is that this operator norm, because I've assumed PC is less than B22, this is just bounded. So it's really just something I can bound by a constant. Ignore it, because I'm looking at things up to PC, right? So, and then we're basically done, right? Because so this is a still low bound on side PFS. Okay. Because this square or one copy cancels with the size of S we had in the denominator. This is just a constant. And then this thing here, well, we know that when the pi of P is certainly blowing up as we approach PC from below, whereas this is bounded. So once we're close enough to PC, this quantity must be at least twice this quantity, and then we get the lower bound. Okay. So I hope this was something that was followable. Again, this is a new proof, so I'm planning on writing this up at some point, and as I said, you can actually turn this into a general proof that the triangle condition implies mean field critical exponents. Just as a remark for experts, the nice thing about this new proof is that it's quantitatively much better than the old proof in the case where this triangle sum is large, say. So the old proofs had all the implicit constants depended extremely badly on the value of the triangle, whereas this new proof is much more reasonable. Good. Okay, so just in the last few minutes, I want to get started on what we'll be talking about mostly next lecture. So far I was telling you about this mean field critical behavior that we expect to hold in high dimensions, and in particular on non-amenable stuff. And as I said, this is still open, although of course we have lots of results in special cases. So what I want to tell you about next is what we do know in general. So as I said, one of the main conjectures is that if you have a transitive graph and PC is not 1, which we actually know now is equivalent to the graph just having superlinear volume growth, then there should not be any infinite clusters of PC. Again, as I said, this is known for planar models and for high-dimensional models, but it's totally open, particularly in 3, 4, and 5 dimensions. On the other hand, in our setting of non-amenable things, this has actually been well understood for a while. So Benjamini, Lyons, Perez, and Schramm showed in 1999 that if you have a unimodular all these results are for transitive graphs. If you have a transitive unimodular non-amenable graph, like a Taylor graph with a non-amenable group, then there are no infinite clusters at PC. We actually now know a bit more than this. So during my PhD, I showed that if you just have a transitive graph of exponential volume growth, this is enough to know infinite clusters at PC. And this used in part an input of the results of Timar, who showed that in the non-unimodular case, you cannot have infinitely many infinite clusters at PC. Okay. And the exponential volume growth, so that again just means that if you take the volume of a ball, it's growing exponentially. This is a bit weaker than non-amenability. It's certainly implied non-amenability, right? Because you have non-amenability says that every set has boundary comparable to its volume, so that implies that balls are going to go exponentially. But you also have examples like lamplighter groups, for example, which are amenable to exponential growth. Okay. So I want to tell you about the proofs of these things. I also want to tell you about some recent-ish work in which we get some quantitative results. So even though we're not able to prove what we'd really like to prove, which is that these infinite dimensional things always have mean field critical behavior, we can prove that they always satisfy some power law upper bounds. In particular, should say this theorem is actually for the unimodular case, although in the non-unimodular case, we actually know that you have mean field critical behavior, so the situation is much better. But the thing I'll tell you about, in the unimodular case, having exponential volume growth implies that you have power law bounds on the distribution of critical classes. Okay? So this is something I hope to be able to show you the whole proof of. So seeing as we have a little bit of time left, let me actually tell you how the main step of this proof goes from this 2016 paper. So really the new thing that I showed in this paper was that if you have any transitive graph of exponential growth, then you cannot have a unique infinite cluster at PC. Okay, that was really the new thing, and then the non-uniqueness was already ruled out by what's already known. First of all, in the non-amenable case, we just knew that there are no infinite clusters, non-amenable unimodular, and then, as I said, Timar showed you can't have infinite clusters in the non-unimodular case. So really, the new thing was to show that you cannot have the unique infinite cluster at PC, and here the proof is so simple I can easily show it to you before we run out of time. So it's going to work by looking at this quantity, kappa p of n, which I define to be the minimal connection probability of points x and y that have distance at most n from each other. And notice that because our graph is transitive, this is really a minimum rather than an infimum, because we only get finitely many different possible values in this quantity. Okay. Now, the first thing we notice is that kappa p of n is supermultiplicative, meaning that kappa p of n plus m is lower bounded by the product of kappa p of n and kappa p of n. And why is that? Well, this is just an obvious consequence of the Euclidean inequality, because if I take some points, if I may as well fix x because of transitivity, if I take some point z with distance most n plus m from x, then of course, I can take a geodesic short path from x to z, and I can find a point y which splits the distance in the right way. So there exists a point y with distance at most n from x and distance at most n from z, like this. Okay, and now I know, right, if y is connected to x and to z, then x must be connected to z. Because these two events are both increasing, they're positively correlated. So the probability that x is connected to z is at least the product of the probabilities that x is connected to y and y is connected to z. Okay, but by definition of kappa, this must be bounded from below by the product. Okay, and now this inequality holds for every z, so it also holds for the minimum limit. Okay, good. Now, this property of supermultiplicativity turns out to be a very powerful thing, and this is used quite a lot in probability. And the power comes from something called Fletcher's law. So this says that if you have a positive sequence of numbers, which is supermultiplicative in the sense of an sequence of positive numbers with an plus n is at least an, right? Then any such sequence has the property that the supremum of an to the power 1 over n is equal to the limit. And this is actually something you can prove pretty easily for yourself if you haven't seen it before. Right? I mean, the point is that if there is some n where this is large, then you have to keep getting something that large infinitely often because of the supermultiplicativity. Okay, so let's see how we can use this to prove the theorem. So we want to prove that we cannot have the unique infinite cluster at PC, and we're going to prove this by showing that the connection probabilities can be between points be made arbitrarily small. So it suffices to prove that kappa actually decays as n goes to infinity when p is equal to PC. So let's start by taking p to actually be strictly smaller than PC, and we're going to use sharpness of the phase transition. Right? So we have by Fekker's lemma that the supremum of kappa p at the end, kappa p of n to the 1 over n is equal to the limit. Right? But this quantity here is the infemal connection probability over a ball of radius n. So it's bounded, obviously, by the average connection probability over the ball, which is this quantity. Right? But now what you see here is that the numerator, which is the sum of the connection probabilities in the ball, well, that's trivially bounded by the sum of the connection probabilities over the whole space, right, which is the susceptibility. So because we're below PC, this is finite, right? So what you get is that when you take the limit, you just get that this numerator just gets destroyed by the taking the power 1 over n, it just goes to 1. Whereas the denominator is the volume is the volume of the ball. So when you take the limit to the power 1 over n, this is exactly the exponential growth rate. Okay, so what you learn is that if p is less than pc, then kappa p of n is always bounded by the exponential growth rate to the power minus n. Okay. Now this is true for every p that's strictly less than pc, but now we just notice that, well, if I look at the probability that x is connected to y, then this is equal to the supremum over r of the probability that x is connected to y inside the ball of radius r. Okay, and the point is that for each r, this is a continuous function, right? Because it's just something about percolation on a finite graph, so it's actually a polynomial. Okay, so connection probabilities can always be expressed as a supremum of some family of increasing continuous functions. And whenever you have a function like that, that's the supremum of increasing continuous functions, it is always left continuous. Right? So connection probabilities are always left continuous in P, and that means that this bound that we proved holds for every P less than PC must actually also hold at PC as well. Okay, so we've shown that at PC, the infemal connection probability decays exponentially in the distance, and just the fact that it decays at all is enough to conclude we don't have a unique infemal connection at PC. Okay. And just to say one more thing before we finish, is that actually you can do exactly the same proof to learn something about P22. Okay, so what you learn is that at P22, the infemal connection probability at P of n is bounded by the growth to the minus n over 2. Right? So before at P we have minus n, here we have minus n over 2. And in particular, this means that in the non-amenable case, say, you can never have a unique infinite cluster at P22. Right? Again, you just do exactly the same thing, except when you get to this stage, you just write this as an inner product, and then you use that it's bounded by the operator norm, which is some constant times the norm of the indicator of the ball, which is like square root of the point. So you learn that there's never uniqueness at P22, and a very interesting open problem is to understand when these two quantities, P22 and PU, the same or different. But I think, yeah, I'm out of time, so
Thank you very much, Tom. Let's thank Tom for a wonderful lecture today.
I had a couple of questions. Yeah, I had a couple of questions. Can I ask? Yeah.
Go ahead. Go ahead.
Right. So I can't recall exactly what we proved about. I mean, for which class of graphs we proved that they have mean field behavior at criticality. But do non-amenable Cayley graphs have mean field behavior at criticality?
Right. So the thing we proved was that this condition PC less than P22 is sufficient.
Right.
So the upshot is that we believe that non-amenable graphs should have mean field critical behavior, but this is an open problem.
Okay.
So,
even for
yeah.
Cayley graphs?
Yeah, even for Cayley graphs, yeah. In fact, as I said before, the surprising thing here is that actually, if you have non-unimodular transitive graphs, we somehow understand these very well now. These are like as far as you can get from Cayley graphs within the transitive world. So it's surprising that non-unimodularity, which seems like a logical property, is actually helping us understand things in this case. I think, if you can understand this problem for Cayley graphs, I'm convinced that your the same proof will solve the problem for general unimodular transitive graphs, and hence the whole conjecture, because we already understand the non-unimodular case.
Okay. Okay, the next question is a bit more vague, I guess. I mean, you commented on the critical exponents for Euclidean lattices and trees. So I was just wondering, what is the case for products of trees and Euclidean lattices? Is it? I mean,
oh yeah, well, yeah. So those things, if you take a product of a tree and a Euclidean lattice, then that would be non-amenable. And in fact, that's actually one of these settings where, although that's a Cayley graph, it actually has a non-unimodular transitive subgroup of automorphisms. Namely, if you so imagine you have the tree times the lattice, you can look at the group of automorphisms that fixes some specific end of the tree, and that's a transitive group of automorphisms, but it's non-unimodular. That actually means you can apply all this non-unimodular magic, and we actually totally understand that example now. Although the proof is not so robust in that it's quite specific to that particular Cayley graph of like the product of a free group with a free abelian group, if you like. So there are other Cayley graphs of the same group which don't have this non-unimodular transitive subgroup, and we don't have to analyze those.
Okay.
Any further questions for Tom?
Yeah, one question, this operator theoretic approach, how much does it extend to say something like a long range percolation models or so? Does it work?
Yeah, right. There's no problem doing it for long range models. It's basically the same. I mean, you just you have to replace the adjacency matrix with the appropriate long range thing. It's all but yeah, there's no barriers to using this. I would say though that for Euclidean models, it seems like you get less out of this approach than in the non-amenable case. I mean, it's still, the notation I think can be useful, but in the non-amenable case, you have this thing that the L2 operator norm is potentially behaving in a different way than the L1 operator norm, which is what you kind of extract all the juice out of. Whereas in the amenable setting, these two norms are always going to be the same. So it's giving you less interesting stuff there.
Okay. And even the sprinkling lemma kind of works, is it? Because sometimes long range you have different probabilities on edges. I was more concerned if there is an issue there.
No, that's totally fine. It's just that you have to. We basically, in the sprinkling we had. This one here, right?
Yeah, this is the lemma. This lemma.
Yeah, it's just that like in this setting, this epsilon times the adjacency matrix is kind of like our sprinkling matrix. But in the long range setting, you just have to replace that by something else, some appropriate other thing which accounts for these long range edges.
Okay.
But it's all fine.
Okay. And for continuum models also, the same thing kind of works approach? I mean, you can define still this operator, right?
Yeah. So if you do, it depends what continuum model you're interested in, of course, but if you do the Poisson Boolean model with, let's say, constant radius balls, so you just have a Poisson process and then each point has a ball around it and you form the graph overlaps. That model you can basically treat with exactly all these tools that you have for Bernoulli calculation apply in more or less exactly the same way to this model. So in particular, all this operator stuff works.
Okay.
If you, there are other continuum models like Voronoi calculation or something like that, where things are much harder because you don't have the BK inequality, for example.
So like Voronoi on a hyperbolic plane or something, it might be interesting, right? Or
yeah, I agree. That is interesting. In fact, this is something I thought I'd solved. So I think in the hyperbolic planes, this is quite well understood, but in higher dimensional hyperbolic spaces, proving that there's a non-uniqueness phase is open. And I thought I had a proof for this, and there's a gap that I never was able to close. So if anyone is interested in talking to me about this at some point, I'd be happy to.
Okay.
There's this gap that we have.
Okay, thanks.
I have a small question. Can I ask?
Yeah.
Okay. So this is a follow-up to the last question, where you said that if for a product of trees, you can decide that PC less than PU because you have this kind of non-amenable subgroups inside the full automorphism group. But could you do the same thing for example? Yeah. So could you do the same thing for I don't know, product of surface groups, but instead of fixing an end, you're fixing a boundary point in the Gromov boundary or whatever?
Yeah, so I think that doesn't work because this non-unimodular subgroup thing is actually, it's very delicate. So normally what happens is if you look at that group fixing a point in the Gromov boundary, it's just not going to be transitive. So what happens in a tree is that the action on the Gromov boundary is transitive.
Yeah.
And this is typically not the case. So with hyperbolic groups, for example, they typically don't have one of these transitive subgroups that fixes a point. In fact, So this is something that's really specific to particular Cayley graphs that have really a very large amount of symmetry.
I see. Okay.
So it's actually known, I think, that basically all groups, there exist Cayley graphs where the automorphism group is just the group. You don't have any additional automorphisms.
Yeah.
And so in particular, when you have a Cayley graph like that, its automorphism group is countable, and therefore it can't have any of these non-unimodular subgroups because countable groups are always unimodular.
Okay, thanks.
Are there any further questions? So otherwise, probably I'll conclude with a more philosophical question to Tom. So Tom, so this generic idea, of proving continuity by obtaining uniform upper bound on quantities all the way up to the subcritical regime. So now you can actually, more recent papers have done for graphs with stretch exponential growth and things like that. So do you think is there any conceptual barrier to push it down to, let's say, high enough polynomial growth? Thus producing a new proof for alternative for the less expansion techniques. Is there any conceptual?
No, I don't think there's any conceptual barrier. This is something I've thought about a lot. I haven't been able to get it to work. But I had this recent paper showing that you can actually apply these similar techniques to long-range models in Euclidean space.
Yeah.
And these models they include models that are supposed to be in the same universality class as nearest neighbor percolation on Z3. And it seems that they don't work, but it's unclear why this is. And one thing I was able to do, for example, is prove some conditional results. So suppose you take 2 points that are at distance 10 in ZD, and let's say condition on the event that they're connected in critical percolation. If you can prove that, let's say the condition on this, the path connecting them has length bounded by n to the million with high probability, something like constant probability, where million doesn't depend on the dimension, then then I can, conditional or something like that, I can prove that in, say, dimension higher than 1 billion, you get continuity of the phase transition. This seems like a very stupid estimate. I mean, this should be like a n squared. But anyway, I've only been able to prove conditional things like this and not able to actually get it.
Great, thanks. Okay, so let's thank Tom again for this wonderful lecture.